Hello, I'm Sungjae Hong from the Mobile Networking Lab. Today, I'm going to introduce the paper called Deep Contextualized Word Representations. This is the contents of my presentation. First, I'm going to introduce the model, ELMo, briefly, and then introduce language model that is based on. Then, I will explain the details and show the result and conclusion. In this paper, they are representing a new type of deep contextualized word representation. The word deep indicates that it is using neural network, and word representation is simply word embedding that models complex characteristics of word use and polysemy. After they explained their model, they tested on 6 challenging NLP problems, which is shown above. They are saying that the model significantly improved the performance compared to the other one. Now, I'm going to introduce the new type of word representation called ELMo. ELMo stands for Embeddings from Language Models. Unlike traditional word type embeddings, this model takes a whole input sentence as a token. Also, they use vectors derived from a bidirectional LSTM that is trained with a coupled language model, objective on a large text corpus. ELMo representations are deep in the sense that they are a function of all of the internal layers of the bi-language models. Before we take into the deep details of how ELMo works, I will explain the main concept bi-directional language model. In this slide, I will mention forward language model first. When given a sequence of n tokens, the probability of the sequence can be achieved by modeling the probability of tokens given the history like shown above. That is what forward language model computes. Each position k, each LSTM layer outputs a context-dependent representation, and the top layer LSTM output is used to predict the next token with a softmax layer. Backward language model is similar to a forward language model, except that it runs over the sequence in reverse. Each backward LSTM layer in J in a L layer produce representations shown above. This is the architecture of bi-directional language model. It combines both a forward and backward language model. On the bottom is the representation of the input. They are usually words. And then we pass it up to the recurrent structures like LSTM and GRU. And they are gonna read the sequence. On the left side, it reads the sequence forward. And one on the right side, it reads the sequence backward. From that, we obtain the sequence of the states of output from the recurrent structure. And the softmax on top is training mechanism. The likelihood of sequence of token, which here is the sentence, is the product of greedy model, which is the probability of any words given or the words that preceded. Now, let's think about how the training works. Let's think that the token we are processing is T1, and forward model has processed to T0 and produces the representation of H0. and the backward has produced output H4, H3, and H2, and then we train that with softmax and try to maximize the likelihood. Now that we train the model, we have good parameterization. Then we have element-wise concatenation of representation of forward and backward language model. Those become the word vector, or we call representation vector. This is the architecture of ELMo. We have sequence of word as T as an input and L layers of recurrent units stacked. And on the top there is a softmax, which is a training mechanism. For each token, a L number of layer of bidirectional language model computes a set of 2 multiply L plus 1 representations. Now we can compute a task-specific weight of all bidirectional language model layers. Here, S task means softmax normalized weights, and R task allows the task model to scale the entire ELMo vector. It's important to aid the optimization process, since the activation of each bidirectional language model layer have a different distribution. In some cases, it also helps to apply layer normalization to each bidirectional language model layer before weighting. Without this parameter, the last only case performed poorly for SNLI, and training failed completely for semantic role labeling. To add ELMo to the supervised model, we first freeze the weights of the bidirectional language model and then concatenate the ELMo vector ELMo task with X and pass the ELMo enhanced representation. We observed further improvement by also including ELMo at the output of the task RNN by introducing another set of output-specific linear weights and replacing the output H with H and ELMo vector. The information we can get from the bidirectional language model is different from global vector for word representation. For global vector, they concentrated in the sport-related sense of play, but the bidirectional language model is disambiguate both the part of the speech and word sense in the source sentence. And the bidirectional language model's input is a sentence. You can see that the nearest neighbors of bidirectional language model is also represented as a sentence. As explained it on previous slide, bidirectional language model senses the disambiguation of words. When the sentence is given, they can use the bidirectional language model representation to predict the sense of a target word by using a simple one nearest neighbor approach. Post-tagging is process of marking up a word in a text as corresponding to a particular part of speech, and they use the context representations as input to a linear classifier that predicts post-tag. And for implications for supervised tasks, this experiment confirms different layers in the bidirectional language model represent different types of information and explains why including all bidirectional language model layers is important for the highest performance in downstream tasks. To do so, we first use the bidirectional language model to compute representations for all words in the corpus, and then take the average representation for each sense. At test time, we again use the bidirectional language model to compute representations for a given target word and take the nearest neighbor sense from the training set, falling back to the first sense from WordNet for lemmas not observed during training. Here are the results. This is the test set comparison of ELMo enhanced neural models with state-of-the-art single model baselines across 6 benchmark NLP tests. We can see that there are improvements on every NLP test when they use ELMo. First, textual entailment is the task of determining whether a hypothesis is true given a promise. The Stanford Natural Language Inference corpus provides approximately 550,000 hypothesis and premise pairs. Its baseline, the ESMI sequence model, uses a bi-LSTM to encode the premise and hypothesis, followed by a matrix attention layer, a local inference layer, another bi-LSTM inference composition layer, and finally a pooling operation before the output layer. Overall, adding ELMo to this ESMI model improved accuracy by an average of 0.7% across 5 random seeds. A 5-member ensemble pushes the overall accuracies to 82.3%. A semantic role labeling system models the predicate argument structure of a sentence and is often described as answering who did what to whom. We model SRL as a value tagging problem and use it on 8-layer deep bidirectional LSTM by using forward and backward directions interleaved. As shown in the table, when adding ELMo, the single model test set jumped 3.2% from 81.4% to 84.6%. Co-reference resolution is the task of clustering mentions in text that refers to the same underlying real-world entities. Its baseline model is the end-to-end span-based neural model. It uses a bi-LSTM and attention mechanism to first compute span representations and then applies a softmax mention ranking model to find co-reference chains. Adding ELMo improves the average by 3.2%, from 67.2 to 70.4%, establishing a new stage of the art. Again improving over the previous best ensemble result by 1.6%. Named entity recognition task consists of newswire from the corpus tagged with 4 different entity types. Following recent state-of-the-art systems, the baseline model uses pre-trained word embeddings, a character-based CNN representation, two bi-LSTM layers, and a conditional random field rows. As shown in the table, ELMo enhanced bi-directional LSTM conditional random field achieves 92.22%, averaged over 5 runs. The key difference between ELMo system and the previous state-of-the-art is that ELMo allowed the task model to learn a weighted average of all bidirectional language model layers, whereas previous one only used the top bidirectional language model layer. It shows that using all layers instead of just the last layer improved performance across multiple tasks. Finally, the fine-grained sentiment classification task in the Stanford Sentiment Treebank involved selecting one of 5 labels, from very negative to very positive, to describe a sentence from a movie review. The sentence contained diverse linguistic phenomena, such as idioms and complex syntactic constructions, such as negations that are difficult for models to learn. ELMo baseline model is the bi-attentive classification, which also held the prior state-of-the-art result when augmented with Cove embeddings. Replacing Cove with ELMo in the BCN model results in 1.0% absolute accuracy improvement over the state-of-the-art. And now the conclusion part. This paper introduced word representation with bidirectional language model, and it showed high performance on a broad range of NLP tasks. Lastly, bidirectional language model layers efficiently encode different types of syntactic and semantic information about words in context, and since ELMo uses all layers, it improved overall task performance. This is the end of my presentation. Thank you for listening.